Ya. Kayaknya kita mau mulai aja sekarang ya. So I think we're gonna start. We're gonna start now. Hold on. Okay. So yeah. Thank you so much. Good morning, everyone. Thank you so much for joining GoJakarta today. We are collaborating with Stockbit today, and we have Mas Edwin here as our speaker. He is the principal engineer at Stockbit. Thank you so much. I think kayaknya gue opening pakai bahasa Inggris aja ya. Jadi yang nggak ngerti maksudnya nggak bisa bahasa Indonesia di sini, jadi bisa catch up gitu. Okay, so we will have Mas Edwin here as our speaker, and let me tell you guys what he's going to present today. So, as I mentioned before, Mas Edwin is principal engineer from Stockbit, and he will present building a performant and reliable stateful data feed service, in which he will explain about the Stockbit design, its performant and reliable stateful data feed services to consumer market, updates from IDX to build its real-time order books functionally. Then a little bit of profile from Mas Edwin. He graduated from Nanyang Technological University, Singapore, majoring in computer science, and previously worked in Shopee as the engineering manager for more than 5 years, and then moved to Stockbit in 2022. Okay, guys, so some of you might be already knows me. I'm Winda. The moderator and host for today. I'm from Brankas, and also I'm handling for this event for GoJakarta like this monthly. So if one of you here wants to be the speaker and might be interested for the job position in Brankas, so you can just reach out to me. And if you want to see the open positions available in Brankas, you can just go to our LinkedIn or our website on the careers page section. Then you can see, some positions that we are still open in Brankas. Then, so later also, Mas Edwin will have a little bit of announcement from Stockbit. So yeah, so don't forget I just want to let you know if after the presentation there will be a Q&A session, and there will be merchandise. For six best questions. So please take a look to the presentation, and then then if you have any questions, just ask on the Q&A session. So yes, Mas Edwin, you ready for the presentation today?
Yep.
All right.
You can hear me, right?
So we'll start now.
Can you hear me?
Yep.
Okay, sure.
All good.
So I'll start then.
Okay.
Thank you, Winda, for the introduction. Hi, everyone. My name is Edwin. Let me set up this thing. All right. So I'm currently a principal engineer at Stockbit, and today I'd like to share how we build a performant and reliable stateful data feed service for IDX. So without further ado, let's get into it. Here's the outline, very straightforward. Basically, I'll give you a brief understanding of how IDX, or the Indonesian Stock Exchange, provides market updates to us and what we plan to build with it. And then I'll introduce our initial architecture, the problems that we had, and how it evolves into our latest architecture. And lastly, I'll give a brief summary of the sharing and a Q&A session. But before that, let's talk about what is Stockbit and Bibit itself. Stockbit, the one at the top, is a stock application with three main features. We have the social networking, information aggregation, and trading. So basically, you can use Stockbit to check some financial news, do some social networking with some investment influencers, look at some statistics, financial data for the stocks that you are interested in. And of course, you can buy and sell stocks too using Stockbit. On the other hand, the one below is called Bibit. It's our mutual fund application. And here you can buy mutual funds, or what we call in Indonesia reksadana, and also SPN, or the Indonesian retail government wants to. For today, the feature that I'm going to talk about is more related to Stockbit. The requirement is very straightforward. We want to build a real-time order book capability. So what is order book itself, right? So here's the Stockbit's order book UI sample. Basically, there are two parts. The one at the top is called the live price, and the one below is called order book section. Okay, so the live price shows the open, high, low, closing average prices, and you can see there's a total lot and value being traded up to the point the data is being shown here. And then the order book section, the one below, actually shows the current bid and ask numbers. So we can use this data to decide if I want to buy a particular stock, then what price should we want to use to buy the stocks or sell the stocks. Now that we know the basic requirements, right, let's take a look at what kind of market updates we can get from IDX itself. So IDX stands for Indonesia Stock Exchange. They provide a few functionalities. Basically, they are the one who is regulating the stock market. They provide systems for submitting stock orders, doing the stock order matching itself. And they also provide a data stream on the market updates during the day using a protocol that we know as the ETH protocol. And this is what my team is interested in to build the data feed service. We want to use this market updates to know what orders are being created during the day and what are the matching mechanism and so on to build the order book data. They actually provide lots of other functionalities, but not really relevant to my topic today, so I'll skip them. Okay, let's talk about the data stream itself and the ETH protocol. Basically, it's a simple binary data protocol, and they have a lot of message types, each defining a certain market update type. And because they have different messages, they came with different data format with different length of the message. We have 3 examples here to show you. The first one is what we call the ETH message. Basically, if we receive this message, it means someone just submitted a new order for a particular stock. So in the body, you'll get the timestamp, an order ID, whether it's a buy or sell, the quantity, the price, and so on. And then when that order is executed, we'll get another message, which we call the ETH or the order executed message. And you can see here that the content is very different from the type A. Let's take a look at one last example, which is the type Z or the index directory. So this is basically telling us in Indonesian stock exchange market, what kind of stock indexes are actually available. So for example, you have IHSG or the LQ45, some of the more popular ones. Dealing with ETH is actually quite tricky. Why is that? The first thing is that some messages from ETH actually contain the full data. So for example, there's this message called the order book directory, which tells us what stocks are available in the market right now, the ticker symbol, the company name, whether it's currently tradable, and so on and so forth. But then, on the other hand, most other messages actually contain only partial data. So let's take a look. What does this mean? If you notice from the previous page, the add order message only contains the order book ID, but not the stock code. The thing is, when we want to show this data to front end, we have to show the stock code, not the order book ID. So when we do the processing, we need to maintain the order book directory data inside the internal state, and we have to refer back later when we get the add order information, add order message. Another example is when the order is executed. If you recall, it only contains the order number or the order ID, but it doesn't tell you the price. So when we want to update the live price, let's say the highest price that we have seen today, we have to maintain the prices of the orders, which means when we get the add order, we have to maintain all the order list that we have seen today, so that when we get the ETH, the order executed one, we can refer back to the order information and get the price, the quantity, and so on. In summary, to build a complete data update when we are using this ETH protocol, we need to have some kind of a barrier mechanism. We have to fill in the data step by step and only update to the front end when the full data is ready. So let's take a look using a simple example to show how the barrier should work. Let's say we are talking about BBCA stock. So in the processor here you can see that we have the current order book state for BBCA, which is empty initially. And before we can publish any order book changes to the front end, we have to wait for the stock info for this stock. Again, because we didn't know that given an order book ID, it's actually BBCA. Okay. So assume we get the stock info here, we store that state internally inside the processor. And then when someone places a new order for BBCA with order ID 10, give him 1 second. Okay. This message, right, contains the price, quantity, and so on. So we'll have to maintain this order details inside the processor internal state as well. Because later, when we get the executed data, the order executed data, we have to refer back to the order ID 10 details. Okay, so now we have to update the order book state for BBCA. And because we have the stock info and the order ID 10 details already inside the internal state, now we can build the full complete updated data, order book data to the front end. Okay, so you can see that there's multiple steps that we have to build and a barrier mechanism before we can push all the latest order book data to the client. So this builds or gives us the idea of how we can proceed with the first architecture, the stateless services architecture. For this architecture, we store the partial states in Redis. We use Kafka consumer groups to decouple the different logics and for horizontal scaling purposes. We only have one each consumer that pulls data from IDX and a few processor instances. And here is how the architecture looks like. Again, we have one single consumer because there is only one TCP connection from IDX. And then we push the data into Kafka. We have a processor just for the bit offer section and another one for the open high-low prices or the live price processor. And again, as I mentioned before, we store the partial data in Redis. For the right side, the Redis on the right side, we have the publish and subscribe, which is how we used to push data using WebSocket to the front end. But this part is not really relevant here. This is here just for completeness. Now, the problem with this architecture is that for every single message, we have to call get and set operation from and into Redis. And the thing is, during the peak hours, let's say during the 9 a.m. opening market hours, the number of messages that we get from IDX can get as high as 100,000 messages per second or even more. So the network round trip and the additional Redis commands actually become the bottleneck. Okay, so to back up my claim, let's talk about how slow is Redis anyway. So we did a simple benchmark between a Redis, map with lock, and map without lock in Golang. Here is the specification on our runner for the benchmarking. Basically, 2 CPUs, 1 GB, and the Redis is using AWS Elastic Cache, 2 CPU, 3 GB. We are testing the get and set operation using the GoTest benchmarking tool. The result is quite obvious. Basically, Redis is much slower than an in-memory map in Golang. Here's the number. Just pay attention to the first row. Basically, Redis is like 3,000 slower than the maps. And maps with lock is still slower than the one without the lock. Even though when I was running this benchmark, there's only one coroutine. So the fact that there's a lock without any lock contention, or there is no more than one coroutines, already make the map with lock slower than without lock. Similarly, the set operation, Redis is way slower again. And the maps with the lock is still slower than the maps without the lock. So this gives us an idea for our next iteration. We want to ditch Redis. We want to remove Redis from the equation. And we want to store the states in memory. And as much as possible, we want to avoid any form of locking. So now we have the first stateful services, the version 1. Now we don't have any Redis. We move everything into in-memory. If we do this, our internal benchmark shows that it improves each consumer by 60% faster, the open high-low close processor or the live price by 40%, and the bit offer processor by more than 2 times faster. But is it that simple though? We'll take a look at some problems that we faced when we are dealing with this stateless architecture. Okay, so this is how the new architecture looks like. It's very similar to the previous one, but now you can see there's no more data Redis storage being used here. Everything is in memory. Okay, the first problem is with the message distribution. Since we are using in-memory and no more memory sharing between instances of the processors, so data of a stop only exists in one instance, and one instance doesn't know that there's another instance exists somewhere else. So we can't get them to aggregate the data properly if we split the data, some partial, let's say BBCA data on instance 1 and another one in instance 2. We can't do a proper data aggregation that way. Okay, so we need to have a way to always push messages for the same stop into the same Kafka partition. And this can be done easily using the key property. I'm using the France KGO Kafka client. If you pay attention to the one below, the kgo.record, we give the topic, the body, and there's this field called the key. If we provide this key with the stock code string, then we are going to be guaranteed it will be sent to the same partition over and over again by Kafka. They are going to use some hashing mechanism here. And don't worry about any other Kafka client library, let's say like Sarama. They should have something similar as well. The second problem is that for some system level messages from IDX, that has to be sent to all instances. So for example, IDX actually sends a reference timestamp to synchronize our system with their timing. That kind of messages has to be sent to all instances, or otherwise we can't really synchronize our clock or our internal timestamp with their time reference point. To handle this, it's more complicated. Here you can see that the first line, the first bolded line, we have to register our own record partitioner. And we have this manual record partitioner function that I implemented. What it does is basically if the kgo.record contains a specific partition, then we are going to use that partition statically. We are not going to use some form of hashing and so on. And then when we are going to produce the data to all partitions, we loop through n times. And when we create the payload, we put the partition specifically into a specific partition. So when this payload is being pushed into the client.produce, it will trigger the manual record partitioner to figure out, oh, okay, you have this payload and you want me to send this to partition 0 only. The whole mechanism will just work here. Okay, so this is similar like previously. I believe Sarama and other Kafka clients will have something similar as well. The second problem is the lock contention problem. When we pull the data from Kafka, let's say we have 10,000 messages from Kafka, it might be quite tempting to spawn a worker pool to consume the messages from Kafka as fast as possible. But that comes with different kind of problems, right? The first one is that we have to maintain the ordering for the same stocks. If let's say we are getting add order BBCA and then execute BBCA and then add order another order of BBCA, we cannot mix and match this ordering, or otherwise the final result of the order book will be wrong. And to solve this, we can use a key and hashing for distributing to the worker queue internally, just similar to how we do the partition assignment in Kafka Producer just now. Secondly, if we have multiple coroutines, that means we have to share some states, and hence we have to use a lock. And as I mentioned in the previous benchmark, maps with locks are already slower even without concurrency. If we add concurrency here, then the number of lock contention will increase, and obviously the performance will decrease as well. So let's use an example here. Let's assume we have a bunch of messages in Kafka. We have a main coroutine for consuming messages from Kafka in that one instance. And then we have two worker coroutines which share the same in-memory state. So we need a lock to protect this in-memory state. Now, say we are consuming the BBRE update number 1. Assume it goes to worker queue number 1, and then BBCA goes into number 2. When the second BBRE update comes in, it has to go to worker number 1 to preserve the ordering. Otherwise, if it goes to worker number 2, there's a possibility that the second update for BBRI will be processed before the first one. The last problem is the biggest one, reliability. The most obvious question is, if one instance is down, then what's going to happen? So the first one, the in-memory state is gone, and we have nowhere else to find the old states. So we have to reset the Kafka offset to rebuild the entire states by rewinding and reprocessing every single thing. Similarly, because we are using consumer group, what will happen if there's a rebalancing here? So there will be a new partition assignment, and that means if an instance was handling partition 0, now it might be getting another partition. And then the state will be gone. They have to do some data movement to reshuffle the in-memory state across instances so that different instances now can continue processing the new partition assignment. And you might be thinking, why don't we just restart and reconsume everything from the beginning? Yes, we can do that, but it takes time to reconstruct the whole state, especially when we approach at the end of the day, because we accumulate more and more messages at the end of the day. In addition, the user will feel like they go back in time because now we are processing from the start of the day, accumulating the total lot, total volume, and so on. And all this data will be shown to the users. So you might feel like, oh, we just go back to 9 a.m., 9:01, 9:02, and so on until it catches up with the latest data by the time. So the key here is to figure out how to rebuild the in-memory state efficiently when there is an instance down and so on. That gives us some challenges when we are building the latest architecture, the stateful architecture version 2. Here's the overview, how we plan to solve the problems before while maintaining the performance. So we need to reduce the locking. We have to drop consumer group so we don't get rebalancing. We have to periodically sync the in-memory state to Redis and load any previous state on startup if available. And the architecture goes back to how it looks like in the stateless architecture, but the way we are using Redis is quite different. Now we don't store the active partial states in Redis, but we only store the snapshot of the state from the in-memory. Let's tackle the first problem, the rebalancing problem. Before that, let's take a look at consumer group, a little bit of a background here, without touching too much technical details. When an instance drops out in a consumer group, maybe it's getting killed, got a panic, or whatever, a rebalancing starts. And when a rebalancing starts, it will trigger a partition reassignment. So as I mentioned before, an instance which was handling partition 0 may now be handling partition 1, 2, 3, and so on. To make things more tricky, when you're doing a rolling deployment, let's say we have n instances and the deployment process takes longer than a particular timeout, which I will touch later, this might trigger multiple rebalancing. And then you have to reshuffle the in-memory states again and again and again, and it's quite expensive bandwidth-wise and time-wise. Yep. So how do we set the rebalancing timeout? Apparently, there is this configuration called the group initial rebalance delay millisecond. What it means is that once a rebalancing session starts, it will wait as long as this configuration timeout for any instance is joined to join. Okay. After the timeout passes, it will do the partition reassignment. And if an instance wants to join after the session is closed, it will trigger another rebalancing session. So as I mentioned before, when the rolling deployment is too slow, then this timeout might has passed away, and then it will trigger a new rebalancing again and again. Let's use an example. Assume we have 2 instances, 4 partitions. Here is the partition assignment. BBCA goes to partition 0, the LKM goes to 0, BBRI goes to 1, HMSP goes to number 2. So the partition assignment looks like this. Instance 1 handles partition 0 and 1, containing BBCA, BBRI, TLKM, and instance 2 handling partition 2 and 3, only containing HMSP. assume there is a rebalancing now, and there's a new partition assignment. So now instance 1 is handling partition 1 and 2, expecting to contain BBRE and HMSP. And instance 2 now has to get BBCA and TLKM. So with this, now instance 1 needs to somehow get the HMSP's last known state to properly continue processing. And instance 2 now needs the BBCA and TLKM state. Okay. So just by doing this, now we need to have 3 state movements between the instances. Now imagine again, if multiple rebalancing sessions are triggered one after another, then eventually all instances might have to move around all their states, and that's quite expensive. You might be thinking, if you know about this feature called the static group membership, basically it allows us for an instance to rejoin the group and get the old partitions assigned to it previously. This sounds like it solves the problem of rebalancing, right? If an instance is down, it's okay, just wait until it goes back up and it will continue consuming from the same partition. Well, yes, but not so fast, because when we use this static group membership feature, we have to assign something called the instance ID. And if an instance ID is killed, the new replacement has to use the same instance ID to get the same old partition assignments. So the question is, how do we generate this group instance ID consistently? How do we know which group instance ID just died and needs to be reused? And lastly, there is something called the session timeout.millisecond. What it does is that if the instance doesn't join before this timeout passes, then when it joins, there will still be a new partition reassignment, which is rebalancing. Okay, so this might happen if, let's say, somehow your deployment process is down or there was insufficient resources to deploy, and then the whole deployment pipeline just gets slowed down. And the tricky part is that how do we even decide what this session timeout millisecond should be, the value, right? Because this is a static configuration. If it is too long, we have a bigger chance to successfully redeploy the instance, but then this configuration is also being used to detect lost instance. So if an instance doesn't send any heartbeat as long as this configuration, Kafka will think that this instance is dead, and then a new rebalancing will trigger again. If it is too short, a slow deployment, as I mentioned before, will trigger rebalancing anyway. So in short, when we are using consumer group, there are a lot of possible problems here. It's very tricky to decide the numbers for the static configurations. A rebalancing will trigger a lot of in-memory state movements, and a simple deployment can trigger multiple rebalancing. So how do we solve this problem? Instead of using consumer group, why don't we use a simple consumer to disable the rebalancing logic entirely? So we use a simple consumer with a static partition assignment, and a single consumer will only consume from a single partition only. The downside is that now we don't have Kafka, or we can't get Kafka broker to maintain the offsets for us. So we have to maintain the last read offset by ourselves. And then when we are creating the simple consumer, we have to tell Kafka, hey, I want to start reading from this particular offset. And then we keep consuming one by one and incrementing one by one. But this is not a big problem, because if you recall, our services is going to be stateful anyway, right? And we have to maintain the order book data, the partial order data, and so on. So this offset is just another additional state that we can store, okay? Let's use an example here. Say we have two partitions with two instances. The instances store the offsets in Redis, okay? And initially, both instances are healthy and consuming messages from their partitions individually. Assume later instance 2 is down for whatever reason. Partition 0 is going to be consumed as usual, no rebalancing happening at all, because instance 1 doesn't even know that instance 2 exists in the whole ecosystem, right? So partition 1 will have no consumer until instance 2 is replaced, but partition 0 will keep consuming as usual. Now, problem 2, the biggest issue. How do we store all these states anyway, right? And here are some guiding questions. Basically, we want to answer these questions: where to store, when to store, how to store efficiently, and how to handle potential duplicated messages. We'll go through these questions one by one. Let's start with the simplest one. Assume we have a copy of the states. Where should we store it? The requirement is very simple. We just need a durable enough storage to last for a day. Why only a day, if you're wondering? Because the next day, for a stock exchange system like this, the state will be reset and we have to get the full data from IDX again. So we can't really reuse the state from the previous day. We have considered 4 options: a SQL DB like MySQL or PostgreSQL, a remote file system or block storage like AWS, EBS, or EFS, object storage like S3, and of course, in-memory remote storage like Redis or Memcache. Since we are in need of a very good write performance, we decided to use Redis. We are using the AWS Elastic Cache, using the master slave and the auto failover for better reliability. And we also have been using Redis before, so it's easier to just reuse our existing infrastructure. And lastly, during the initialization time, if an existing state is available, then we have to try to load that existing state first. The next question is how to store the states efficiently. First of all, we cannot store the state after every single message. That will bring us back to the stateless architecture. So we have to store the state periodically. But how do we define a single interval or a single period, right? There are 2 options. It can be time-based, which means we store the states after every n seconds, or it can be counting-based, meaning we store the states after processing n messages. Now, this tool has its pros and cons. With a time-based, maybe it's more intuitive, but we need a locking mechanism between the timer coroutine and the main one when accessing the internal states. With the counting-based, we don't need a locking mechanism, but if we put n as 500 messages and let's say our consumption rate is very slow, it might take a few seconds or even minutes to generate a new snapshot. Okay, but this whole process will be synchronous, so we don't need any locking and so on. Whichever method that we are using, we have to choose the value n. The intuition is very simple. With a smaller n, we'll have worse performance as we have to do the state snapshotting more frequently, but we will have more chance to store the very last offset. And when we restart, we don't have to replay too many old messages. On the other hand, or the reverse, with bigger n, we do less snapshotting, we can consume faster, but we have to deal with replaying more old messages on restart. To decide this data, this value, we add some metrics and take a look at our own use cases, what would be the good value, and how to build the deduplication mechanism, which I will explain later. So now we have that. Let's talk about how to copy the states efficiently. Regardless of how frequent we store the state, we have to find a way to copy the data, the full state efficiently. And we have to copy the full state in a way that we don't block the main coroutine from pushing it to a remote Redis while it's pushing to a remote Redis. Problem statement is very simple. Given a map of n items, what is the fastest way to create a new map with a shallow copy? The first one, just use a normal hash map. The second one, there is a fancy data structure called the concurrent trie or C-trie. A short background about the concurrent trie. Basically, it's a concurrent version of a hash array mapped trie or the HAMT. Basically, it's a hash map implementation using a tree where the hash of the key gives you the path into where the data should be stored in a tree node. And by doing that, it can create a constant time snapshot creation because it doesn't copy the whole tree on snapshot creation. Instead, it copies just it points into the root node and only update the data when it is needed. So if you just create a new snapshot and you don't update any of the data, there is no additional cost there. I'm not going to touch too much on the details here. If you're interested, you can take a look at this paper from the original author, concurrent tries. I think this is quite an interesting paper. The idea is quite similar to how the immutable.js actually work. So if you are interested in it, you can take a look by yourself later. So we did a simple benchmark here, comparing the hash map and the seed try with different number of n, or number of items. If you take a look at the number, it's quite obvious that the concurrent try, regardless of the number of n, is much faster than the hash map. A normal hash map is slower because it's an O of n operation, or linear time complexity, while for seed try, it's a constant operation. So it doesn't matter how many items you have. This is because, again, seed try will just create a new pointer pointing to the same tree root, and it only updates when it is needed. But when we look at the cat performance, you can see that a normal hash map is way faster, regardless of the map size. This is because in seed try, there are a lot of concurrency check, like the atomic swap, compare and swap operations. It has to traverse through the tree. Although the height of the tree is not too deep, it's still an additional overhead. Similarly, set operation, a normal hash map is still way faster than a concurrent try for the same reason. So how do we decide? At the end, we decided to just use a normal hash map because it has a faster set and get, which we use more frequently than the copy operation. And sometimes for a single message, we have to call it multiple times as well. We don't have any need for the concurrent access to the map. So an additional synchronization logic in seed try is just an additional overhead for us. And lastly, although the copying operation is much slower in the hash map, we are only doing it infrequently because we can adjust the number of n in the counting or the time-based periodic mechanism. In fact, if we want to do things more smarter, we can even disable the copying during the peak hours, like at the market operating hours. And this ensures we can deliver the updates as fast as possible without being affected by the state snapshotting process. So after we have this, we have to handle the duplicate messages. Okay, in what situation we can have this problem? Well, for one, what if the instance get killed abruptly? The latest in memory might not be stored in Redis yet, including the offset. And after the new instance is up, it will check the last seen offset, but it's not the very latest one. And then we'll have a duplicate processing. We'll read the same messages and reprocess the same messages. Let's use an example here. We assume we store the state per 2 messages. Okay, now we have 4 messages in the partition 0. There is no latest offset yet. There is no last offset in the state snapshot as well. We process M00, update the internal state, latest offset state to 0. And then we continue to process the second one, M01, update the internal latest offset state to number 1. Now that we have already processed 2 messages, it triggers a state snapshot. So we push the last offset into the Redis. So you can see that Redis has the last offset of number 1 as well. We continue processing M02, update the internal latest offset state to number 2. But let's assume at this point, after we process 3 messages, this instance is now killed for whatever reason. Okay. And after some time, a new instance will be spawned for this instance number 1. And the new instance will have to ask the latest known state from Redis. It says that the last known offset was number 1, which is inaccurate because we actually already processed number 2. And when we ask Kafka, we are asking the next offset is number 2 again. So we are going to process M02 for the second time. And this might cause some inaccuracy in our order book page. How do we solve this problem then? We solve this by attaching a sequence number for every single message. The sequence number will be added by the each consumer service because IDX doesn't provide one. And it starts from 0, just monotonically increasing. And you don't have to be worried about this because it won't hit the integer max limit. The way we are using this is very simple. The processor has to maintain the last processed sequence number. It has to, if we find a message with a smaller sequence number than what it has seen, then we can safely assume, oh, I've already processed it and I can skip those messages and go to the next message. But then this is still not a perfect solution. Why? Because if the processor dies, then there won't be any place to deduplicate the messages. No one will know what was the accurately last processed sequence number in the bigger scheme of things. So the processor will still push messages into Redis PubSub. The user will see some old updates. Secondly, what if multiple components are down at the same time? We cannot be sure who has the more accurate state. So basically, this is a trade-off between accuracy of state snapshot and performance, just like any other engineering problem. In summary, let's have a short recap of the solutions that we have chosen. First of all, we store the state snapshot in Redis. We are using the master-slave configuration with auto failover for better reliability. And then we try to load any existing state at initialization time, if any. We use a hash map, a normal hash map instead of ctry, because we don't have any concurrency logic, and the additional synchronization logic is just an unnecessary overhead. Yes, the copy operation for in-memory hash map is slower for copying data, but we only copy data infrequently, so it's an acceptable trade-off for our use case. The frequency depends on what you need. We could have a time-based or count-based logic. Both have their pros and cons, and you can decide the frequency based on some data that you can collect according to your use cases. Lastly, we have potential duplicate messages in some edge cases, but we try to minimize this by handling a deduplication logic by adding a monotonically increasing sequence number. Each instance has to maintain their own last processed sequence number. When an incoming message comes in, they can check against their last sequence number that has been seen and recheck if the new message sequence number is lower than what they have seen. Okay, that's quite a lot of information. Let's do a short summary of everything. From the start, the goal is to build an order book feature by consuming the IDX data stream. An order book is basically showing the current price, the high, low, open, close price of the stocks, the total lot, total value, and the latest bid and offer numbers. We started by building a simple stateless services with Redis as the main storage, but this architecture was too slow because we have to reheat Redis for every single message, and the additional overhead for network and the Redis processing is too slow. So we figured out that putting the states inside the services in memory is much, much faster. So we built the first version without thinking about the reliability first, just make it as fast as possible first. And lastly, our latest architecture, we thought of all the potential reliability improvements while maintaining the performance as much as possible. And how we do that? First of all, we don't use consumer groups. We use a Kafka simple consumer because we don't want any rebalancing to affect our performance by having too much state movements. We store the state snapshot into Redis. We use a normal hash map for better overall performance instead of using the concurrent try. We built a deduplication mechanism by using the sequence number for every single message. So that's how we built a performant and reliable stateful data feed service. Before I end the presentation, last but not least, Stockbit is currently looking for Golang developers as well, especially for this trading team. So if you are interested in working at Stockbit and dealing with this kind of interesting problems, please follow us and check out our career page as well. So yeah, that's the end of my presentation. I think we can open the floor for Q&A. So back to you, Winda.
Okay, thank you, Mas Edwin. So guys, if you have any questions, please raise your hand or you can just type in the chat here. So we have Mas Gary Nugraha raised a hand. So yes, Please unmute yourself, Mas Gary. You can ask
Hi.
to Mas Edwin.
Yeah, hi, Winda.
Hi.
Can you hear me?
Yep.
Okay. Yeah, hi, Edwin. Nice to
Yeah.
see you again. So, yeah, great presentation overall. My question was just that I understand that your choice of like using in memory versus like the concurrent reads because of the performance, right? But I see the benchmark that both of them it's still like more than tens of thousands of requests a second. They can handle more than that. So I'm just considering like, is it worth it to just get like the normal hash map that can do like 1 million requests a second compared to just like the concurrent one, which can do 100 million, but I'm not sure whether that's like the real bottleneck in the system. Yeah.
Let's take a look at the number just now. So you're saying that one is at the millions and then the other one is at 100 millions, right?
100,000. Yeah.
So yes, I think for our use case, it does matter because we are looking at micro performance improvement that even though it just shares maybe hundreds or thousands of nanoseconds, actually it accumulates, especially when we are talking about during the market opening hours. I mentioned earlier, it's actually 100,000, but in reality, it can be up to 200,000, 300,000, and so on. And that's just in the first millisecond. So it's not really, let's say we are talking about 300,000 on the first second. It's not really 300 uniformly distributed across milliseconds for that 1 second. But in fact, actually, it's on the right side. On the first few milliseconds, it will come at around 300,000, 400,000 milliseconds. Messages. So to answer your question, yes. And at the same time, if you recall that each consumer, there's only one instance. So, and we can't really add more because it's a data stream, right? So you can't really have multiple IDX connections because the ordering might mess up, and IDX doesn't really support like multiple partitioning like Kafka. So yeah, unfortunately, we have to think that way.
I see. Okay. Yeah, if 300 in 1 second, that gives us a better perspective. Thank you.
Thank you for the question, Mas Gary. Hope it answered. And second question from Julian. She or he got 2 questions. If the same stock code will be processed by the same stateful processor server, what happens if there is a stock that has a lot of orders? For example, like Boomi several months ago. Before we move, maybe you can answer first, Mas Edwin.
Yeah. Good point. If that's the case, then one of the partition will be a hot partition. But the thing is that we already tried to benchmark this, and so far we don't really have a problem of having a hot partition. But if you're talking about what might happen if that one hot partition is getting too hot, right? I think that there could be some smart ways to handle this, which I haven't thought through very carefully. But the idea is to probably have a more dynamic way of partitioning the data based on previous day's data. But this itself cannot be accurate because it could be like today, there could be some hot stocks that we didn't have any pattern previously. So in that case, I think we can only scale up the instances and see what happens. But for, let's say, some stocks that we know have more transactions per day for the past, let's say, 7 days or something, probably we can do some data analysis and saying that, because this particular stock is too hot for the past 7 days, we can have a separate partition just for that stock. And for the stocks that have lower number of transactions, we can put them into separate stocks as well. So that kind of distribute the partitioning probably better distribution. But yeah, this is probably a hard question to answer without having data.
Okay, so let's move to the second question. Please hold on, Mas Altiano. Out of topic questions. Why use WebSocket instead of server? Send events for order book? Because in my opinion, order book receives data much more than it sends data.
I'm not sure what this means actually. Order book receives data from who and sends data to who?
Maybe Mas
Can we
Julian, you
get,
can open your microphone, then ask, like explain about the question, please. Is Mas Julian still in the call? Yes.
Okay, if
Okay, we just move. Oh, okay.
oh.
So, okay. Order book receive data from server to client more than send data from client to server.
Okay. Server to client. I'm not sure server send events. This is using what, HTTP2, like push mechanism, or
Maybe Mas Julian, you can add again. Yes, only server data to client.
If you are talking about HTTP2, I think I'm not entirely sure, but I read there are some problems with the server push mechanism. I need to go back and check first. And then actually WebSocket is fine because as you mentioned as well, we push more data from server to clients. I don't think there is any particular reason at this point yet, to be honest, because HTTP2 probably have their own problems, WebSocket has their own problems, but I feel it's just a trade-off that we decided to choose WebSocket at this point. Yeah.
Okay. Okay, before we move to Mas Sandi, please unmute yourself, Mas Altiono, you can ask.
Hello, can you hear me? Yeah, thank you. So first of all, it's a really great presentation, Edwin. That's a lot of information to digest. And so I was wondering whether in the first part of your architecture, where you consume events from IDX, you're using the each protocol, right?
Yeah.
So I would like to know a little bit more about this protocol. If you could explain to me whether that's first of all, is it like just a streaming protocol where there's only like one-way communication where it only comes from IDX and you cannot send like a request or something like that? You know what I mean? Like fetching more information, but you only reading information. So that's kind of like the first question. But then also like I'm curious about your way of consuming these events. Like I only see the like a single process when consuming the stream of events. Like I was wondering whether if that process fails, and then you might lose some events, right?
Okay, understood.
Is there any backup server or something like that that you put in place to avoid that kind of unfortunate events? Like it's kind of like the second question. Yeah, thank you very much.
Okay, the first one, no, actually we can push data to the TCP side. Sorry, to the IDX side. So there is this protocol we built. How to put it? The each protocol has a transport layer protocol called the sub-pin TCP. So it's basically on top of TCP, but they have a more specific way of defining the message structure and the lock-in mechanism and so on. So when we are connecting to them, we have to push some binary data saying that, hey, I'm this guy, this username, this password, and I'm going to log in and I want to read from a particular sequence number. Okay, so that's to answer your first question. So we have to send heartbeat and some data from time to time between me, Stockbit, and IDX, right? So that's the first one. Second one, reliability-wise, why only one TCP connection? Because again, it's a data stream. So the way we pull data is using binary packets, right? So it will tell you, hey, I have this new binary data. The length is, let's say, 100 bytes, and then we are going to read the next 100 bytes. This is the each message. And then depending on the each protocol or the message types, you can slice one by one to understand the field of the each message. Okay, so that's how we read the data. Why only one TCP connection? Because I believe that's how currently is being set up by IDX. And if every single TCP connection consumes the same data, then there's no point to have multiple instances as well, because both will be reading the same data, right? And in terms of the reliability, yes, if we go down, actually, we can just respawn a new service, and this new service can tell IDX that, hey, I was this guy who previously read up to sequence number 1000. Now I want to continue to 1001. And that's how we can just continue without any lost messages. Yeah, I hope that answers your question.
Oh yeah, that answers. So that's some kind of like in Kafka terms like offset
Yes,
kind of
correct.
thing. Oh,
Yeah.
I see. Yeah. So if I may add one more question, so because I was really curious with this it's protocol, like is it a free protocol where anybody can just use it, or is it some kind of
Yeah. Protocol wise, I think
yeah.
it's always free because it's just protocol, right? It's just like you have gRPC, you have protobuf, and then you can build more protocol on top of it. But I think I'm not sure what's your use case if you want to use it, but yeah, you
I want
can
to
always
like
use this.
ingest data from IDX. If I
But you
that
have to pay
use it.
for that. Like you need to get some connection from IDX because it's additional resources for them, right?
I see. Okay.
Yeah.
Okay. Great information. Thank you.
Thank you.
Thank you, Mas Altiano. So we're going to move to Mas Sandi. How about Golang GC? Does it affect app performance?
Yes, obviously, yes. So we did some improvement. Let's say because we can afford to get more memory, we can reduce the GC percentage. GoGC, tuning the GoGC environment variables. That's one thing. And second, I would not use string as much as possible. So let's say we are going to have a map of a stock code into some data. I'm not going to use the stock code because string is an additional pointer and it will get garbage collected, or at least will be checked or scanned. So my suggestion is use very basic data types like Boolean, integers, floats, and those kind of things. So as much as possible, try to reduce your pointers. Yeah, and that actually helps. And we do some object pooling as well. We try to reuse the object as much as possible. Yeah.
Okay, thank you, Mas Edwin. Then from Tirumalesh, is there any sample app in GitHub to understand building stockbroker from scratch or any papers?
Honestly, I don't know. I've been trying to find one, but I can't find myself. So we have to figure it out myself. But if you're interested, I think you can try to open YouTube as well. Some big, what do you call it, like stock institutions, companies, they sometimes explain things, but usually they do it in a far bigger scale than us. Let's say for the stock, US stock, usually they have more transactions. So they have to use things like C, C++, or even Java, which is probably not so relevant to Stockbit's use case. So I haven't found any good references that I can share as well.
Okay, hopefully it helps and answered your question. Then, sorry, to Mas Hardi. Is there only one instance of running Golang binary or process that consumes the ITCH protocol data stream from IDX? Or is there a single data stream that duplicates data to multiple instances that then process it?
One instance, one binary. We don't really duplicate. Because of the reason that I mentioned to Mas Altiano just now.
Okay, so this recording or presentation will be shared.
I don't think so. I'm not sure. Yeah, but actually it's in the YouTube, right? So I believe you can.
Yes.
I'm pretty sure it's accessible later as well.
Okay, so from Reynaldi. Hi, I've got two questions. You haven't talked about any memory management issues while tackling the streaming data from IDX service. Do you ever encounter any stop the work garbage collector issues, Or do you ever encounter any data loss caused by the garbage collector cleaning up some stuff? And by the end of the day, during the closing time, how do you handle the data cleaning up for the consumer so that it don't really clog much memory for the next day?
Yep.
That's the first question.
Yeah, let me answer this one. Ever encounter stuff the word? Yes, of course. I think that's how Golang garbage collection works. Data loss, I don't think so. If there's a data loss because garbage collection is running, I think there's a very big issue with Golang itself, which I don't think is happening, or at least I'm not aware of it. By the end of the day, during the closing time, how do you handle? I think we can just restart the server, right? Because we don't really need the data from the previous day. And for the second one, I think I can just explain this right away. Yeah, we can switch. We can just update the IP address and restart the servers. So I think it's quite simple to for the reliability side of things. Yeah.
Okay, for the second question, during an incident caused by the ID Extreme service, all stock brokers are required to switch.
Explained already, actually.
Oh, okay.
Yeah.
It's done. All right, any other questions? Please. Oh, if there is someone who wants to connect with you, so should they just send the invitation through LinkedIn, or do you have Twitter or anything you can share?
Oh yeah, I don't really use Twitter, but you can ping me on LinkedIn. Yeah, if you want to ask me more questions, you can just post messages into my LinkedIn. Yeah.
Nice. Okay, please contact through LinkedIn. Okay, any other questions? We still have time. So, Mas Edwin, how many questions do you want to answer again if there is questions coming in?
Maybe 3. I mean, depends on how complicated the question is. But yeah, I think 3 is fine.
All right. So, yeah, any other questions, guys? Before we announce the winner for the merchandise from Bibit. From Bibit or Stockbit, it's the same, right?
It's the same company.
Okay. Okay, we're waiting for 2 minutes for the other questions. Okay, Mas Cesar, do you have any question? Oh, I think accidentally unmute, yeah. Okay. Okay, still open for the questions. Oh, well, I got a question for Mas Edwin, yeah. So, what's the reason you moved to Stockbit, and do you enjoy being in Stockbit now?
Okay. Previously, I was in Shopee Singapore, right? And I've been in Singapore for almost 10 years since I've been studying there at NTU for 4 years, and then I've been working at Shopee by around 5.5 years. I think the first reason is because it gets boring in Singapore. There's nothing else I can explore anyway, so that's the first reason. And secondly, I've been looking at Indonesia as a growing tech company. I mean, you know, there are a bunch of big tech companies here, and I saw there are lots of opportunities in Indonesia. So I've also been interested in the finance industry for a while, and I've been looking at Stockbit and been using for a while. And I feel like Stockbit is at an interesting point in their growing path. I think Stockbit has a lot of potential to grow in the future as a company, as a business, and its engineering team is at a time where it's going to grow even bigger, and they will need some help, or maybe it's something that I can contribute more in terms of how they build the culture, the engineering excellence, and based on my experience being in Shopee, going through such a very fast growth from 2017 to 2022, right? When I joined Shopee, it was around like 100 people, and then it becomes probably like 5,000 engineers and so on. I feel there are certain experience that I can bring to Stockbit as well to grow their engineering team. And maybe the other part is that I want to be in the driver's seat to build and shape the engineering culture. So that's why I joined as a principal engineer. And although my official title is principal engineer, my day-to-day role is both principal and engineering manager. And this is an interesting, a very rare combination of roles, right? Because when you are principal, usually you don't become an engineering manager. But because I have both experience, it makes my day-to-day job easier because now I have bigger influence on both the management and the technical side. Yeah, so that's how I feel why I joined Stockbit.
So do you still thinking maybe someday you will go abroad again if there is any changes? Or do you want to, okay, I'm enough. I'm just staying in Indonesia, something like that.
I think going abroad doesn't mean that you don't work for an Indonesian company, right?
Okay.
So
We still can
I
work
don't see a
remotely.
reason why that is not an option. But at this point, I don't see I'm going to go abroad yet. Yeah, at least for 5 to 10 years. Yeah.
Okay, nice. Okay, there's questions coming in again. First from Raymond. I've got a question. If I don't recall it wrong, Stockbit use WebSocket to stream data from server to client, right? Order book and running trade are two different things. So does Stockbit open two WS connection or just one, but parse it on the client side? Thank you.
Just one. I don't see a reason to open two connections yet. So yeah, the answer is just one and parse it on the client side.
Okay, Mas Raymond, hope it helps and hope it answered your question. Then another question from Hardy. And infrastructure-wise, you've said that for the ITCH processor, there is only one instance. What is the infra support for that one single binary? Also, are the other parts of the architecture, OHLC and bit over handled the same way? Example, one process or any they handled differently?
Not its processor, but its consumer only one instance. Yes, the support, I'm not sure what do you mean by support, but we are using orchestrator. So if it's going down, then the orchestrator will take care of the responding and so on. And for the processors, handled the same way. Yes, Kubernetes, we are using Kubernetes for the orchestrator. One process, no, we can have multiple instances because it's using Kafka partitioning. And as long as the ordering of the same stock messages are preserved, then you can have as many instances as possible. Yeah.
All right. So hopefully it answered again your question. So do you like to announce the winner? I mean, like the first question. Yeah. Okay. Well, to be honest, I like the first question from Mas Gary. If you're okay with that, so we can choose that one also. Mas Gary, thank you so much for the question. And for the other, maybe you can choose Mas
Renaldi.
Renaldi, okay. So Mas Gary, Mas Renaldi.
I think Altiano.
Altiano, okay.
And
then, okay.
I think Mas Hardy, this is a quite good question. Yeah.
Hardy.
Yeah.
Okay.
And I can't recall who asked in the call.
It was only Altiano and Gary was raising the hand.
Then probably, yeah, I think that's all from my side.
Okay. Okay, so we got like, okay, Mas Gary, Altiano, Renaldi, Hardy. Right. Okay. So far we got one name. We got 4 names for the merchandise. Thank you so much for the questions. And please reach out to Stockbit Bibit Live in Instagram. So you can send the direct message for your name, your address, phone, and email. So you can just contact the admin there. Then they will present the merchandise to you. Don't forget, the address. Don't forget about this. Then okay. Any other question? Any other things you would like to announce, Mas Edwin?
Not from my side. I think it's just to remind again that we are still hiring Golang engineers. So if you're interested in this kind of probably anti-patterns if you compare them into other industry technological side. But these are very interesting problems that I was surprised myself when I joined. So yeah, if you are interested, please join us.
Nice. Thank you so much. Also, I thank you so much also for Stockbit for having, for giving us the chance to collaborating for GoJakarta this month. And if there is one of you wants to be the speaker for GoJakarta, or if you want to take a look to our open positions in Brankas, please, you can reach out to me to my LinkedIn, and or you can just send me an email. I'll share you my email here. Yeah, so hopefully we can keep in touch. Mas Edwin, thank you so much. Mas Dika, Beli Nyoman, Mbak Putri, Mbak Jessica, thank you so much for your time and for arranging this GoJakarta with Stockbit today. And hopefully we're looking forward for the further collaboration in future with Stockbit. Jangan kapok. Thank you so much. So I think that's all for GoJakarta today. It was fun session with Mas Edwin and very interesting topics also for today. So yeah, thank you so much, everyone. See you again next month. Please check on the updates on our meetup.com for GoJakarta, and we will surely announce the upcoming events there. Thank you so much. Wish you have a great day. Enjoy. Bye.
Thank you.
Everyone.
Bye.
Thank you.